we find a conformal boundary, and this boundary has a topology of a torus, so the formal ADS is just a solid torus characterized by this modulus. And this torus is not general because the modulus is pure imaginary. It means precisely that if we realize this space, I mean, if you realize torus as a rectangle on a two plane with identified edges, so in this case we have very particular rectangle without twists. Now this is my final slide, and first of all consider the case of zero-point conformal block. That is, we just switch off the external leg, and in this case the corresponding graph is given by a circle running around this dashed line, which correspond to zeroth radius, and the total action is, in this case, is given by two terms. The first term is the gravitational action evaluated on thermal ADS, and the second term is the circumference of the loop, which can be easily computed from the metric on the previous slide. So in this zero-point case, we find this expression in terms of tau, and coming back to modular parameter, which is related with tau by this formula. Tau is just proportional to logarithm of q. So we see that this is the logarithmic contribution seen on the previous slides. And if we switch on the external leg, we also can show that more general duality holds. And in this case, this arm has three terms, including the length of the leg, and the correspondence, what is more important, holds in the so-called low temperature approximation. This is because we know that on the gravity side there are a lot of saddle points parameterized by different values of the modular parameter, and the formal ADS corresponds to infinite modular parameter, contrary, say, to ETZ black hole, which correspond to zero modular parameter, and they are related by modular transformation. Okay, so our claim is that the block length correspondence in this case is valid in the low temperature approximation, where the temperature is just in gross modular parameter. So now let me summarize, and we consider it torus conformal blocks, and observed that there are four different types of semi-classical blocks, and we established a chain of connections between these different semi-classical blocks and explained the appearance, the appearance of semi-classical blocks from the Virasoro algebra perspective. Also, we holographically realized the one-point torus blocks and the corresponding geometry in the bulkage of the thermal IDS, and the correspondence holds, as I said before, in the low temperature regime. So there are also some open questions. Unfortunately, I have no time to do this now. Thank you very much.
For instance, for the torus, with one insertion you have anywhere to with the matter in the adjoint. This is the simplest example I can think of.
It's not unequal to...
so the class of partition functions, if there is any via some GT conjecture, I don't know.
No, the claim was that one-point torus blocks are related to four-point sphere blocks. So there is a complicated map which relates these two functions. Particularly, it would be interesting to understand how...
No, I was referring to the fact that the conformal blocks or the correlation functions are related via some GT conjecture, you may think, to the Nekrasov partition functions. So it's Cyber-Witten theory, partition, but with the supergravity backgrounds.
You mean AGT duality?
Yes, AGT.
For us, it's just a calculational tool, actually. We suppose that we have some some expression for conformal block, and this expression can be obtained in various ways. It can be done using Zemologica recursive procedure, it can be obtained by using AGT, combinatorial representation, or monodromy method, but for us it really doesn't matter which way we use it. We need the final expression for this function. We have not seen it yet because we know that correlation function is modularly invariant, but conformal blocks are not. So it would be interesting to check how these modular transformations of conformal blocks are reflected in the bulk. So how going between different saddle points of gravitational actions using this modular transformation is reflected with modular properties of conformal blocks. It's open question actually.
We don't have any other questions.
Thank you.
Next would be about problems in aspect.
Of integrability, yes. So this is first of all, thank you to the organizers for putting up this conference and for allowing me to talk here. My hope is definitely that I can actually use all this time at JGI to continue further this work, because there's just too many unknowns. So I'm just going to motivate all the work that we've been trying to do ever since. So this work is basically what's contained in the paper of already a year and a half ago. Well, we've tried many different things from then on. Unfortunately, there's more unknowns than actual full understanding. So the main idea is that, I didn't try this, so I am focusing on strings in ADS3, cross S3, cross T4, and I will be studying basically classical string solutions and their semi-classical behavior, and trying to compare to what integrability tells us that these behaviors should be. And in particular, we were very much interested in circular strings, because they live in the sector of R cross S3. It's very well known what the semi-classical behavior is. It was calculated for this background. And basically, well, it's R cross S3, so they have the normal shape, which is written here. The charges can be written in terms of the it's sum of RS, CRS1, GR plus S, and then QR plus 1, QS minus QS plus 1, QR. So these are all classical charges. So in terms of the classical charges, so it has a closed form expression, and if you expand this expression, of course, what you get is what I've written there as the delta E1 loop. So this was the calculation that was done to, in fact, determine in the ADS5 process 5 to first determine the CRS ones, because they knew what the classical circular string, the semi-classics were, and they could determine the CRS ones. In this case, meaning we already know from other methods what the CRS ones are, and we can actually determine what delta E1 loop is in terms of those CRS1, the one loop perturbation to the dressing phase. And what happens is that, well, if you subtract these two solutions, of course, you get something that is completely non-zero. So we were baffled by this for a long time, and what in fact we found is that the exact reason why these two results don't match is that the massless sector actually plays, not the massless sector, but the mixed mass sector, so the interaction between massless particles and massive particles actually plays a role in the perturbative energy correction, semi-classical correction. And where does this contribution come from? From wrapping. So what actually happens is, well, our claim is that it does come from wrapping, and what we did was do some, we can say, somewhat crude calculation, in the sense that it doesn't include or exhaust all contributions to the semi-classical energy, but is definitely of the same order, more of than of the same order. It's actually of the same shape as the results, the mismatch that we find. And it comes from the fact that when you have massless virtual particles winding around circle L, and you calculate, field theory calculation of contributions that can be done from Lucher. So here I should write Lucher F terms. What happens is that typically these wrapping contributions would be exponentially suppressed, and exponentially suppressed where the exponential is, the top of the exponential is kind of proportional to the mass. So if you don't have a mass, and I'm going to go back to whether you could actually, whether each one of these contributions actually makes sense on its own, but let's assume that we could just take the massless limit of some of these Lucher F contributions, F-term contributions. So if you actually have a massless particle going around the circle, it will have some contribution that will be leading, that will be of the same order as the perturbative contributions that we're calculating. So if it was massive particles, massive sector, they would just decouple and be exponentially suppressed. But if you have massless virtual particles going around the circle, these are of the same order and will actually contribute to the final result. So with this, this is the mismatch, and where do the Lucher F-term calculations? I've presented here some particular solutions, but I'm going to talk a moment about Lucher, and basically the The Lucher F-term calculation originally came for a relativistic theory of particles of mass. I'm going to write S, and with the dispersion relation, so it's relativistic, so the dispersion relation is naturally and you can write this in terms of course, of a rapidity, theta. And you take the volume of the space part, so this was originally in R11, but you then take this to be R. And what you calculate is corrections, so corrections such as this, so you have a particle with momentum p, you have a virtual particle with momentum q. You sum over all possible virtual particles, all possible types of virtual particles. So here it's type B, type A. They might be all of the same type, they might be of different types. Some are fermionic, some are bosonic. And this, basically, well, d2q over 2 pi squared, this function, e minus I. This is the momentum, q1L, and then you have AABB, so this is the vertex, fourth vertex. But what happens if you take L very large is that you can actually rewrite everything and write the vertex as being on shell. So what happens is that for very large volume, you actually substitute the vertex by an S matrix, and you get the original F term, which is so in terms now, this is in terms of the rapidity. So this is for and then you get extra contributions, of course, because I considered one loop, but you can consider higher loops. Some of them will come with double exponentials, double integrals, so you'll have a whole string of contributions. So one thing, of course, this is very hand wave, but if you think that if you're taking S goes to 0, you basically have, what's going to happen is that you can actually have some sort of contribution here from S goes to 0 that is not going to be exponentially suppressed. This is not, meaning it's not that all the integral is not going to be exponentially suppressed, because in fact what shows up in the integral is minus IQL, where you define Q in terms of, it's Q star, where do you define, just 1 second. Minus IQL, so Q is Q of Q star. So Q star is going to be the momentum. This is going to be the energy. And what happens is that typically you have something like this, where the minimum of that exponential is going to be in the mass S. But if you have S goes to 0, basically the minimum goes to really 0, and at this exact point, the contribution will be non-exponentially suppressed. But this is for relativistic theory. So for our case, some calculations have been done. So the first calculation that I'm going to mention is that so Heller, Janicke, and Bukovsky actually calculated the F-term contribution from sum of fluctuations. So they actually assumed fluctuations above some string background. The string background that they chose is just a single excitation, a Magnon excitation, and they assumed that they had a virtual particle winding around the cylinder m times. So they actually not only one, but m times. And you can see that the exponential comes with the m times. So the leading one would be basically m equals 1, and then the other ones are even subleading. All of them are exponentially suppressed, at least with mass equals 0. And the leading one is m equals 1. The other ones would be more exponentially suppressed. Also, from a TBA point of view, so Beinok and Janicke actually calculated you'll have basically a leading contribution, yes. So you would have to actually sum every single contribution that you could think of any particles going. The leading, well, all of them are of the same order. All of them are of the same order, exactly. So this is why I'm saying that our calculation does not give the full result as much as it shows that, at least up to the order that we calculated, that it definitely contributes to the exact same order that mismatch appears. So again, from the TBA, so Bajnok and Janek actually, what they've done is assume the multi-particle state of particles of type A, and assume now one virtual particle winding around the circle L only once. And they calculated, they expanded the TBA basically, and they calculated, so there's a, well, maybe I'm not, so basically in the TBA you have that, first of all you have that the energy of some Ni particles, depending on L, is equal to M where the epsilon of theta prime, so the theta i's are defined, properties of the solutions are defined by the poles of the integral. And you have also that epsilon of theta is equal to m L quotient theta plus sum of the log of the S matrix of theta minus theta j. So this is for relativistic theories. So this is the kernel, which is the log, the derivative of the log of the S matrix. And this is a nonlinear integral equation that defines epsilon iteratively. Of course, if you have a mass scale. So if you have a mass scale, m, you can actually see that you can keep on solving the epsilon of theta kind of order by order, and you basically the next order will be exponentially suppressed. This is not quite true, of course, if you have massless. Actually, if you do the related TBA for massless case, you can, meaning this mass scale gets reabsorbed, disappears, and you do not have a mass scale. What you have to do is actually to solve these equations and see if the solution that you get for the epsilon converges at some point to a particular value, or if by any chance, meaning you could just have in such a way that you couldn't find a solution because every time you try to iterate in some way, you don't get any convergence. But when you don't have a mass, especially massless TBA, basically you cannot use you cannot anymore use the mass scale to actually do the iteration. No, you can actually define a massless TBA, and you can show, I thought that, so, it could not be, exactly. Exactly, so for the massless TBA, what happens is that this one will include every single one of these wrapping corrections, of course, and you can't separate them. So, and for the massless massive TBA, if such a thing can be found, it's the same problem. So, This is TBA, and what they found is that by using the same methods, they could find a multi-particle state on the outside of physical particles and one virtual particle going around once. What happens in our case is actually, so circular string. The circular string is a multi-particle state. But as I mentioned, for sure, if we did just one winding, why would I choose one winding instead of 2 or 3 or n? Because they're all of the same order. So what we tried to actually do, the calculation that we tried to do, well, first we did one winding and we saw, we obtained results that are of the order that we want, but the coefficients are definitely incorrect. What we did was like a kind of adjustment between this formula and this formula, which is what is written there, which is a kind of multi-particle physical state and sum over n windings. In such a way, because again, all the windings are of the same order, so we don't have any gauge of choosing small winding or large winding. And by using the mixed mass sector, so the S now that is written there is basically the S matrix being a massless virtual particle and a massive excitation out of these K excitations. And you can actually do the calculation. And what you find, sorry, I just want to not only we find the right order of the results, but we also find, in fact, the same general shape of the expansion, apart from a factor of 2. Again, coincidental, not. So our guess is that if you actually manage to really do the full TBA for that includes the massless massive sector, that somehow any other contributions other than just winding of particles, of massless particles m times, need to somehow cancel, because the shape is the same, so it's, or they all contribute to cancel the factor of 2. This is not completely obvious, but it's not, but definitely there's some, meaning these contributions, just these contributions seem to already be of the correct shape. So I would like to finish with a set of we've tried, of course, many different checks and tweaks to what we were calculating to see first if we could determine the factor of 2 apart from actually determining the full TBA. So one of the things is that, for example, in terms of mismatches, circular strings in SU2 are not the only ones that have a mismatch. So we have the SU2 circular strings and we have the SL2 circular strings. So here we have that the K is basically a L over 2 J charge, so in S3. The SL2K is S charge, so ADS, also L over 2. And in this case, if we do the same calculation, again, we get the correct order, but we do not get the correct coefficients. So it's not, meaning it's just a factor of 2 times the mismatch or anything of the type. Huh? No, in this case, even even each term doesn't match, the coefficients don't match. So we get the correct 1 over J cubed, 1 over J fifth. So it's the correct orders, but the coefficients actually are not the same. So we get K minus M to the cube time, meaning because here for the SL2 you have both K and in the winding M for the resolvent, and the coefficients definitely do not match. So also we need to make sure that we don't break the agreement that you can find for the SL2 short strings and also for the giant magnet. So it seems that meaning if you have very large multi-particle states, that there's a mismatch, but if you don't have such a large state, there is agreement, and definitely meaning this needs to be taken into account. Somehow the massless particles do not cancel out their contribution. And of course, there's all of the other terms that if you did the massless TBA, and meaning if you had a massless massive TBA, and you could actually, instead of doing an expansion of this log, actually do the whole calculation with the log, you would get all the massless contributions. And in that case, the hope would be that you could actually determine the full difference between the string semi-classical calculation and the beta-Ansatz massive sector calculation. So that's basically it. So this formula is definitely a trial formula, even not. It's just a kind of trying to do a multi-particle state with an N winding. Of course, with the winding, meaning if you can see here, we didn't assume massless scattering, so that we would get kind of a -1 to the N if we did N winding, and we considered the -1 to the N. In fact, for the calculation of the circular strings, it doesn't contribute because the odd terms actually are 0 in the calculation, so it doesn't make a difference. But once again, that formula is just, how do you say, a prototype of what multi-particle physical state with M winding would be. And we would have, well, again, for the massless sector, probably we wouldn't even have full Lucier contributions because they don't separate. So these are all the open questions, trying to understand everything. Unfortunately, for most things at the moment, more things don't work than they do. So we're still stuck with how to deal with the massless sector, and how the massless particles actually contribute to the semi-classics of strings in this background. Thank you.